Hello, Jennifer.
Hello, Sean.
Sean, yes, your husband. This is us speaking to each other somewhat artificially. I'm in my office at Caltech.
And I am in my home office in downtown Los Angeles.
That's right. And so, but we can pretend for, internet purposes that we're thousands of miles away. It wouldn't make any difference.
Exactly. That's the beauty of the internet.
And have you been to any good parties lately?
That is such a lame segue. Yes, because of course the big news the last week was the turn-on of the Large Hadron Collider, and it was a lot of fun for me because, I actually went out to Caltech, sat around with the scientists late at night with beer and pizza waiting for the LHC to turn on, and for people like me, that's kind of a different experience. We don't work in science, and we don't often get the chance to kind of share these sort of exciting events. Although I have to tell you, as far as turning the actual machine on, it's not as cool as a rocket launch. It was kind of like the big countdown that we had to look at this sort of computer screen that looked for all the world like the game Pong, and then there would be a blip, and everyone would cheer.
Well, yes,
and
it was.
Maybe what you can do is explain to the people out there why that was so exciting, because it is when you stop to think about what's really happening. But I think that it might have gotten lost on some people.
Well, it was the whole setup was very amusing, of course, because through the miracle of time zones, the people at CERN had a day's worth of activity planned. But they're in Switzerland. We're talking about the Large Hadron Collider, this giant particle accelerator that just turned on in Switzerland and really represents the future of experimental particle physics. And they've been planning it for 25 years, and they just had a big day where they officially turned it on. The actual turning on process is a very gradual thing, so they picked a milestone event, which is the first time that protons went all the way around in the ring. There's a big ring full of superconducting magnets, 17 miles across, and protons zoom around in one direction, and other protons zoom around in the other direction at very, very high speeds, close to the speed of light, and they will eventually be smashing those protons together and looking to see what happens, with actual collisions, which did not happen on last Tuesday, I guess.
Which I think a lot of people didn't realize, that this was really just putting the first beam of protons through.
They were the CERN people were a little bit cagier than I think they needed to be about what exactly was happening on that first day. And but the point is that, of course, they had a day's worth of activities from 9 a.m. to late in the evening. 9 a.m. Switzerland time is midnight, or 11 p.m. Yeah, midnight West Coast time in the United States, and 3 a.m. on the East Coast. So many Americans missed it, but many of us here on the West Coast who were sufficiently interested stayed up late at night and tried to watch the actual turn-on event. And the disaster, of course, not the disaster, but there was this webcast that people were supposed to be able to look at live, and somehow they only arranged for 2,000 channels on the webcast. 2,000 connections were allowed, which was much smaller than the number of people who tried. So many people just didn't get to see anything at all. So you should count yourself lucky for that.
Yeah, I got to see something.
Yeah, we at Caltech had a special live hookup with our Caltech physicists who were located at CERN working on the collaboration. And we at least got to see what they saw. And there was a video feed from the main CERN control room, which, like you said, was a tiny bit anticlimactic. They were zooming protons around, and the way that it worked is they would... the whole ring is divided up into 8 octants. I almost said 8 quadrants. 8 different octants, 8 different segments. And they would send it through one octant and then stop the beam there. They would just dump the beam and then say, well, did it work? Is everything doing okay? And then they would send it through 2 octants, then 3 octants, and eventually made it all the way around. And, in fact, they were completely sure it was going to work. They had more or less tested everything to death beforehand. But this is the official opening of a new era in particle physics, and we're all very excited.
Right. I just got to warn you right now, the cat is very, very interested in what's going on, so if you...
The cat would like to be vlogging it, that's okay.
So, I'm trying to kind of hold her off, but if she suddenly, walks in front of the camera, don't be shocked.
Right, that's okay. I can't see you, so I have no idea.
Yeah, well, just when it finally airs, if there's a cat that suddenly appears.
Okay, we'll deal with that.
Anyway, what will the LHC find? This is something that's been covered a lot in the press. Obviously, the obvious answer is, of course, the Higgs particle, often called the God particle, which leads many people to think that, in fact, the LHC is looking for God.
Right. It's not. That would be a very unexpected thing to
It would
find.
be very unexpected to find God at the LHC.
But I think actually it's worth, backing up a little bit just to say why particle physicists are so excited about this experiment. Because there are experiments that happen all the time, and this is one particular one. And what is special about this one? And the answer is that it's been a very unusual time in history as far as particle physics has been concerned the last 25 years, because in science you have this competition between the theorists and the experimenters, right? Mm-hmm. The experimenters are trying to find new and unexpected things. The theorists are trying to explain them in terms of models and theories that they will then test against the data. And usually it's sort of, neck and neck. Sometimes one is ahead of the other. So if the theorists are ahead, that means that they've explained things, and they make new predictions, and the experimentalists go out to test them. If the experimentalists are ahead, that means they've found things the theorists can't explain. And it's been very strange, because it's now been like 30 years since the theorists have pulled ahead. The theorists put together the standard model of particle physics in the 1970s. And since then, the experimental particle physicists have just been confirming it over and over again. And that's really boring if you're an experimentalist. And it's also really frustrating if you're a theorist, because you would like to move beyond your theory, but you don't have any experimental clues to do so.
Well, isn't part of the problem that we just don't have the technology to test some of this stuff?
Well, we haven't yet.
Right.
That's the idea. So the LHC really represents the first particle accelerator that unambiguously will be peering into a realm beyond where the standard model has any right to work. So it could be that the standard model is still correct and the LHC peers beyond it, but nothing new shows up. But many, many physicists are convinced that it's much more likely that we'll peer beyond what the standard model claims to describe and find new things, and that those new things will be clues to what goes beyond the standard model.
Okay. But the Higgs, of course, is part of the standard model. It's like the last missing link.
Yeah, so the Higgs boson is a particle that gets a lot of PR as what the LHC is looking for. And I think it probably gets too much attention, frankly. It gets mentioned all the time because it is, like you say, the one thing that is part of the standard model that we haven't found yet. So non-scientists, when you say, we want $10 billion to build a machine, do an experiment, they will say, what are you going to find, right? They want to know what is going to be the answer. And the correct answer is we don't know. Mm-hmm. We don't know because we haven't done the experiment yet. That's the way science works. If we knew ahead of time, we wouldn't need to spend the money. But people don't want to hear that. So we do have this ace in the hole where we can say, well, we really hope to find the Higgs boson. This is one particle that we know either the Higgs boson exists or something exists that does the job of the Higgs boson. And hopefully those things are within the reach of the Large Hadron Collider.
And the job of the Higgs boson is, of course, to give particles their mass.
Right.
Brian Greene had a really nice op-ed in the New York Times just this week that I thought, he used a really, really good analogy of how the Higgs does this, how the Higgs field or the Higgs boson works. And you may want to actually, explain to us the distinction, because you hear Higgs field, you hear Higgs particle. Mm-hmm. But essentially it works like, molasses or something, and that things that are really, really heavy have a hard time moving through molasses. I think you might explain a little bit better.
Well, I think that's the basic idea. The point is that the elementary particles in the standard model, the basic building blocks of matter, are quarks and leptons. The up quark, the down quark, the top quark, etc. The leptons are the electron and its heavier cousins, and also the neutrinos. And together, those small set of particles make up everything made of ordinary matter in the universe, whether it's you or me or some interstellar cloud or some other planet far away or some cosmic ray. And it's all quarks and leptons. The quarks go into making the protons and neutrons. The leptons are lighter and zoom around them. But the interesting thing is, if you take seriously the symmetries that exist in the standard model, they make a very unambiguous prediction that there should be no mass. These particles should be massless, which means, according to relativity, they must move at the speed of light. But as a matter of fact, they don't move at the speed of light. These particles have a mass. You could sit them on a scale and weigh them. So something is giving them mass, even though the symmetries of the standard model would appear to forbid it.
It would have to be a really, really tiny scale, I'm just saying.
It's a very tiny scale, yes, made of a couple of little things. And so the answer, we don't know what the answer is. We don't know how the electron gets a non-zero mass, why it's not massless. But the answer that works so far is that the symmetries of the standard model are broken. just like you have rotational symmetry. All directions of space are created equal as far as the laws of physics are concerned, but here, standing on Earth, we can tell the difference between up and down. Why is that? Because there's a thing called the Earth that is breaking the symmetry because it is there as this big lump of thing. It matters whether the Earth is up or down. Likewise, in particle physics, we think of the symmetries that would keep the electron at zero mass, moving at the speed of light, is broken by something, and that thing is the Higgs field. The Higgs field pervades space. It exists even in empty space. And the best analogy for it, like Brian used, was molasses, some fluid that takes effort to pass through. So without the Higgs field there, the electron would be zipping along at the speed of light. With the Higgs field there, it's like the electron is moving through molasses. It's slowing down. It takes more effort to push the electron, and that shows up to us as mass.
Okay. I had a very, very interesting question on my Twisted Physics blog for Discovery News. Someone basically posted a comment saying, well, this Higgs field is a little bit like the luminescent ether that was very common in the 19th century. That was back when scientists thought that light needed a medium through which to travel, much like sound waves. And, of course, the famous Michelson-Morley experiment disproved that. But it's not quite the same thing. I mean, when we think of, field means something very, very specific to a physicist, and we tend to think of these things in terms of actual substances or mediums when they're more mathematical realities. So what's real to you might not be the same thing that we would consider real. Maybe you could answer that guy's question. What is the difference between something like the ether? I mean, the molasses analogy is very useful, but again, it's very easy to think that we're talking about an actual substance, when in fact we're talking about a field, and a field has a very specific meaning.
Well, we are talking about a field. I would actually say that it's okay to think of fields as being actual substances.
Okay.
I mean, they're real. They're what the universe is made of. 100 years ago, in the early parts of the 20th century, this was the big debate, is empty space just empty, or is there something there through which waves move as excitations? So, and I think there's this weird compromise answer that says, well, yes, there is something in empty space, but that something is not made of something else. If you talk, the ordinary way of thinking about waves, we think of waves moving through water, waves moving on the ripples of a pond or something like that. And so there, the wave is an excitation of this underlying stuff, the water. And people liked that idea. They didn't like Isaac Newton's idea that gravity, for example, just worked magically across large distances without anything happening in between, say, the sun and the earth. That they didn't like. They didn't want that. And it turns out that there's a compromise, that there is no such thing as the ether. It is not true that light waves are ripples moving in some substance that we could measure our velocity with respect to. But there is something in between the Earth and the Sun. There are fields. There's the gravitational field. There's the electromagnetic field. And in fact, in modern quantum field theory, everything is made of a field. The photon, that particle, is just a ripple, an excitation, a wave in the electromagnetic field. A graviton is a wave in the gravitational field. A quark is a wave in the quark field, etc., etc. So all that is a lengthy preamble to saying that the Higgs field is different from the other fields that we talk about, because if you said, what is the average value of the field in empty space, for every other field the answer would be 0. If there's no electrons in a box, you're saying that the value of the electron field is 0, etc. But the Higgs field has a non-zero value even in empty space. So there's like what we call a Higgs condensate. There's Higgsness there in empty space. And that is what breaks the symmetry of the standard model of particle physics, the fact that there's a Higgs field sitting there even in empty space.
Okay.
And that is kind of ether-like. That resembles that picture of the ether. The difference is that you can't measure your velocity with respect to it. If you're moving through molasses, you can put out your hand and you can feel the molasses going by.
Sean?
Yep. Are you
I
still
lost you there for a minute. Anyway, continue.
Yeah, you can feel molasses going by if you move through it. You can't feel the Higgs field going by. It seems the same to every observer moving at any velocity whatsoever. So that's the way that they reconcile the ether idea with the reality of relativity, which says you can't measure your velocity in empty space.
Okay. And this kind of leads into something I've always been interested in, because we talk a lot about the fabric of space-time. And again, I mean, it's a nice, fun way to talk about it. It's a good analogy. It's a nice metaphor. But we're not actually talking about a fabric. We're not talking about, Egyptian cotton or silk or a cheap polyester blend. We're talking essentially about a mathematical framework on which we are hanging physical phenomena, I guess, for lack of a better word. So, I mean, again, this is a difference in how people like me and an actual scientist might think. I mean, we don't think abstractly, we don't think mathematically, but that doesn't mean we can't kind of get the idea. So maybe you could talk a little bit about what we mean when we talk about the fabric of space-time.
Yeah, I think that there's two things going on. One is that, of course, the attempts to explain concepts that have a very specific technical meaning by using words in the natural English language are always going to be fuzzy, right? We use analogies and so forth, and that's not a flaw. That's just the way it is, because either you're going to learn exactly the whole technical spiel, which takes many years of graduate school or whatever, or you're going to get some description of it in terms of words, and the description can be better or worse, but there's always the danger that when you describe it in words, meanings come along with that description that you didn't intend to bring along. Mm-hmm. So when you say that the Higgs field is out there in space and moving through it gives some ponderousness to elementary particles that we detect as mass, that makes you think of molasses or something like that. And molasses is a little bit different. Molasses is made of molasses atoms and molecules. Mm-hmm. So likewise, the fields that make up modern physics are in fact the fundamental things that the universe is made of. There's a gravitational field, electromagnetic field, etc. So if you go really down to the basics and ask a physicist, what is the universe? According to our best theories right now, the answer is a set of fields obeying the rules of quantum mechanics. That's what the universe is. And what that means is that at every point, there's a number, a set of numbers. There's a number that says, what is the value of the electron field? What is the value of the photon field? What is the value of the gravitational field, etc., etc. At every single point in space. And those numbers can change from place to place, and that's what we call the fields. And this is a deep concept, which I don't know whether it has much resonance with people who are not used to thinking of sets of numbers existing at every point in space. The people try analogies. They say, well, in the room, in your room, you have air in it. At every point, that air has a temperature, right? So that's a field. The temperature is a number that exists at every point. But that's a really lousy analogy because the temperature isn't a thing that can vibrate. The temperature is a property of the underlying air, and that's the difference. Mm-hmm. In this case, when we talk about fields in particle physics, that is the universe. Those are the fundamental building blocks. They're not made out of anything else. When we say fabric of space-time, like you say, it's not that space-time is woven together out of some underlying substrate. Space-time is the thing that is there, as far as we know right now.
That's actually kind of mind-blowingly cool.
Good, it is cool, yes. And I think that, it also explains all of the troubles that people had years ago between particles versus waves. Mm-hmm. The answer... this never gets explained very accurately. The answer is waves. That's the answer.
It's what?
When you want to say waves,
okay.
Is light a wave or a particle? It's a wave. But quantum mechanics says that when you look at something, you don't see it as it really is. You see certain properties of it that are just a subset of what it can be. And the way the particles come into the game is that when you look at a field, you see particles. So what is really there is a field. When you look at that field, you see it as particles. So what is really there is an electromagnetic field. When you look at it with a detector, you see photons, etc., etc. Mm-hmm. And that's how the universe works.
As far as we know, yeah.
As far as we know, yeah, sure. I mean, it could always change. And so the Higgs boson, the Higgs particle that the Large Hadron Collider is looking for, is the particle that is associated with little tiny ripples in the Higgs field that fills space, as far as we know.
Okay, that clarifies things. I think that a lot of people will suddenly go, oh, that's what they mean. At least I hope so.
Yeah.
Now, there's other things that may or may not come about. And obviously the ones that I keep hearing are, supersymmetry and extra dimensions and things like this. But you had actually written a very long blog post over on Cosmic Variance with your predictions for what you think the LHC will find. And maybe you could, pick a couple of those to talk about, what are some of the really exciting things that maybe they aren't likely, but what would really kind of shake things up if we found these things?
Well, I think that in fact it's the other things besides the Higgs boson that really get most physicists excited about the prospects for the LHC. And let me just emphasize one that is very plausible, which is dark matter.
Oh, right.
We live in a universe where through measurements in astrophysics and cosmology, we have verified that the ordinary matter of which you and I are made, the matter that is made up of particles in the standard model of particle physics, atoms made of quarks and leptons, is not enough to account for the stuff in the universe, not by a long stretch. It's only 4% of the energy of the universe. Something like 25% of the energy of the universe is another kind of particle called dark matter, and something like 75-76% of the universe, 70 or 71%, if I'm going to get my math working correctly here, is dark energy, which is not even a particle. Dark energy is more like one of these fields where it's a property of space-time itself. It's a number that exists everywhere.
So you think that the LHC could actually create dark matter?
Absolutely.
Say like WIMPs.
That's right. So the dark matter is, we think, a particle. It acts like a particle. It falls into areas where there's a strong gravitational field. It evolves in a certain way that seems very particle-like. But it is not any of the particles that have already been detected. None of the particles that are in the standard model of particle physics fit the bill for being a good dark matter particle. So it's got to be something else. And it turns out that when you sit down and write a little set of equations saying what kind of particle would have the right properties to have the right density to be the dark matter, you find that the most natural answer, not the only possible answer, but the most natural answer is one that has a mass that should be within reach of the Large Hadron Collider.
Okay.
And these are these WIMPs,
Right.
weakly interacting massive particles. They interact through the weak interactions of particle physics. They're hard to find so far, but this is what the LHC is good at. So the LHC could very well get to a high enough energy to make a dark matter particle. So we wouldn't just be saying, look, most of the stuff in the universe is dark matter and dark energy because we feel its gravitational effects in the universe. We'd be able to say, look, we made it. We can test this idea. We can determine its properties and figure out whether it should have the abundance it does and so forth. So that's an extremely exciting possibility.
Right. Okay. One of the obvious questions, of course, that I keep getting asked is, this came up years ago with the discovery of the top quark. I was at a Christmas party. I was talking to a guy, and he was very interested in physics, but he honestly did not understand how we can tell we've seen something like, say, the top quark when it's so tiny. We're talking about a subatomic particle. And I ended up having a very long discussion with him about, signatures and decay patterns, that essentially these subatomic particles are created in these collisions. The heavier ones decay into lesser, like the top quark, will decay into lesser particles, and it's those decay patterns that sort of comprise a telltale signature. And what's really amazing to me is just the sheer amount of data and how complicated these things are. It's amazing that we can find anything at all. That essentially these particle physicists have some of the best data mining tools on the planet, I would think.
Absolutely. I mean, and the flip side of that is that it's going to be a tremendous challenge at the Large Hadron Collider because they're going to get much more data than they've ever had before.
And aren't they, correct me if I'm wrong, but my understanding is they kind of have to pick the regions of interest and throw out quite a bit of the data.
That's right. So every, I forget the numbers, but every time two protons collide in the Large Hadron Collider, it makes something like a gigabyte of data, if you collect it at all. And like you said, what is happening is the two particles collide, and they give off a shower of other particles, and they create much heavier particles than the initial protons themselves were made of. And that's just the miracle of relativity. E equals mc squared. We have a lot of E, the energy, so we can make particles with a very high mass, a very high m, times the speed of light squared. So we make heavy particles. What heavy particles tend to do is decay very rapidly. And so what they do, if you look at pictures of Large Hadron Collider detectors, they're they're series of cylinders embedded inside each other. They're nested cylinders because what they're doing is building different kinds of detectors to measure different kinds of particles.
Okay.
So you have, the ones that decay the fastest need the sort of most delicate detectors, and they put those in the middle, and the ones that are going to last for a long time, they can put detectors to look for those out at the edges. And there's different technologies for doing it, which is why you have different kinds of experiments being built at the different places at CERN where they're going to be smashing protons together.
And I take it they do have some kind of idea of what they're looking for when it comes to things like the Higgs and to WIMPs. They kind of know that there's a range of things where it could fall, and it's going to focus on those.
That's right. We've not been completely idle for the last 30 years while we're doing this. So people have been building models and working hard. But again, it turns out to be hard. And so every collision is a gigabyte of data. They get something like 1 billion collisions per second. So
wow.
You just can't. There is no technology that would allow you to take all of that data and write it to a disk or something like that, or to tape or whatever. And even if you could, it would be too big. You could never search through it. You would have no idea what's going on. So instead they have something called a trigger. So they have an event in the detector. They look at it very, very quickly, and the hardware decides, is this an interesting event or a boring event?
Oh.
Most events are boring. They just create particles you already knew about.
Right.
And if it's boring, they just let it go. They don't record it. They don't keep it. They keep about 1 in a million events. So 1 millionth of the total data they produce, they will actually keep. And that's still a tremendous amount of data, which they will then search through very, very, very carefully. So, yeah, a big part of the industry is making sure you know what to expect, so you can know what is a surprise and what is not, where to look and where to ignore.
Mm-hmm. And, of course, we have to talk about the mini black holes. Now, I
have no idea what you're talking about.
I know, it never gets talked about in the press.
Yeah.
And I'm going to start by saying, that it's been very disheartening to me that that this whole doomsday scenario, that it really, despite scientists' best efforts, despite people like me who are really out there saying, look, this is not a realistic scenario, it nevertheless became the predominant narrative for the LHC. So much so that pretty much we had no choice but to make it a joke.
Maybe you should explain what the narrative is.
The narrative, of course, is that the LHC will create these mini black holes, and instead of, as one might expect, according to Stephen Hawking, who is the one who came up with the idea that black holes actually evaporate according to how heavy they are, and the lighter they are, the faster they evaporate. So even if a little mini black hole is created in the LHC, it should evaporate in fractions of a second. There's some very long-shot fringe theory that it could be a stable black hole and it would start to suck things in and grow and basically devour the universe. And in fact, there was a lawsuit filed by a couple...
Let's be careful. It'd be just devour the Earth, not the universe.
Devour the Earth. But, once it starts...
Don't be an alarmist.
Once it starts... But, people didn't really make that distinction. That's the thing. But even so, it caused a couple of guys who didn't really even have PhDs in physics, one was like a nuclear engineer and the other was something else, to file a lawsuit trying to stop the LHC from going on, despite the fact that there had been 3 or 4 separate safety assessment reports by some of the best particle physics minds in the world.
Yeah.
And nonetheless, despite the fact that we had all these people out there, countering the message, that this still became the narrative. I don't know what to say about that. As someone who's in the media, it's very, very depressing for me.
Well, I think there's blame on both sides. On 3 sides. One side, most of the blame goes to the crackpots, and they really are crackpots. These people do not know what they're talking about. They're not respectable. There's no respectable scientific reasoning that leads you to believe that anything that happens at the LHC would endanger the Earth at all. Second, there's blame that should accrue to scientists, because bless their hearts, scientists like to be precise. And if you ask a scientist, do you know for sure, do you know with absolute certainty, like you know that 1 + 1 = 2, that something that the LHC will do would not destroy the Earth? And a good scientist will always say, no, I don't know for sure, that probably is very, very small, but I don't know for sure.
Right, and to a journalist, that's just not getting a straight answer.
That's right.
It can be very frustrating to someone who's not used to dealing with scientists, that you ask them a direct question, and they pretty much equivocate all the way throughout.
Right.
And you say, yes or no, I just need a yes or no answer, and they can't do it.
We don't, right. And the answer might not be yes or no, especially when predicting the future.
Right.
But then, like you said, there's also the journalists get some of the blame also because, but there, it's just such a compelling story. So it's been amazing to me how sticky the idea of destroying the Earth has become as regards the Large Hadron Collider. You ask people on the street, what about that giant atom smasher in Switzerland? They will say, "Oh yeah, destroy the Earth." That's what they think of.
Right. Yeah.
And, of course, every story, though, about the LHC turn-on had to mention that or even talk about very little else. Mm-hmm. And so, anyway, maybe I can actually tell people who might still be alarmed why this is not something.
Yeah, there's some people hyperventilating out there right now, so you should
about.
probably calm them down.
That's right. So there's two things you should know. One is that there's nothing that will happen at the LHC that hasn't happened elsewhere in the universe many, many, many times over. So even if you throw away everything that we know about physics, about quantum mechanics and general relativity, number one, it's very unlikely you'll make a black hole in the first place. But let's imagine you make a black hole. Let's imagine that Hawking was wrong and the black hole is stable and it's still stable. Okay. Well, there's no reason to believe that, but let's imagine. So that's a theory. That's a hypothesis that makes predictions, and you can use that. And one thing you would predict is that when you look at astrophysical objects like white dwarfs and neutron stars, these are hit by high-energy particles all the time. They're hit by cosmic rays. Cosmic rays smashing into a neutron star have a much higher energy than the protons smashing into each other at the LHC will ever have. And you can just sit down and do the calculation that says, well, if you would make a black hole at the LHC, what would happen to these neutron stars and white dwarfs? And the answer is they would all have turned into black holes by now. Yet, we see them. They are there. They have not turned into black holes. So this idea is just wrong. The experiment has been done. The black holes are not stable. They do not beat things up. The LHC is safe. Mm-hmm. That's the first argument. The second argument is, because people will still say, but I don't understand, because there's some risk, and the stakes are large. You're going to destroy the entire Earth. Why would you ever take that risk? Mm-hmm. So I've invented a story. And the story is that it's completely analogous to you going home, making dinner, boiling some pasta, and you're about to open up a jar of tomato sauce for your pasta.
I hope it's Prego, because that's my favorite.
It could be Prego if you like. Wednesday is Prince Spaghetti Day, not Prego. But so imagine that you talked to a biologist before you opened up your jar of spaghetti sauce, and you said, is there some chance that when I open up this jar that inside there's mutated a deadly, deadly virus that will kill me instantly and wipe out all life on Earth within the next 2 weeks? If the biologist is as careful as we physicists are, then they would say, yes, there's some chance. It's astronomically likely. It's very, very unlikely. It's nothing to worry about, but there's some chance. And yet, you are going to go ahead and open that jar of tomato sauce. The point is that when you talk about these astronomically small risks, even though the stakes might be very high, sometimes the risk is so astronomically small that we have to ignore it, Like someone said that the Large Hadron Collider could make giant man-eating dragons that come out and eat us all up. There's many things that could come out. The chances are not zero, but the chances are so small that the best we can do is to ignore it.
You know what the headline tomorrow is going to be in the National Enquirer?
Physicist
says LHC will create giant man-eating dragons.
I need to come up with something. Yeah.
So it actually always reminded me, the one that I use when I talk to people is that scene from the Jim Carrey movie Dumb and Dumber, when he's his love interest. He's the idiot. He's in love with this really beautiful woman. And at one point he finally asks her if there's any chance on Earth that, they will ever be together. And she hedges, and she basically just says, maybe if we were the last two people on Earth and there were no sheep. And of course what she's really saying is not a chance in hell. Right. And what he hears is, there's a chance.
You just have to...
That's all he hears.
But as a journalist, what do you think? When if you're a TV reporter, let's say, and the LHC is turning on tomorrow, and you know that everyone in their mind is thinking, destroy the Earth, what do you do? What is the right strategy that you want to keep people happy but also tell them the truth?
Well, this is where, there's something that my friend Chad Orzel over at Uncertain Principles calls lying to children. Yes. It's an oversimplification. It is not the whole truth. And I've been accused of this in my first book, Black Bodies and Quantum Cats. And it's true. I actually oversimplified things because certain things, people just not only, it's not that they can't understand it, but they would not understand the distinction. I mean, they're still trying to figure out the basics. And so I think that it is perfectly fair. There was a line in a movie with, I can't remember what it was called, The Verdict, I guess, which had Sally Field and Paul Newman.
Paul Newman, yeah.
At the very end, the last line, it's basically about the difference between truth and accuracy. And she finally, at the end, ends up being the subject of an interview, and someone asks her about an allegation, says, "Is that true?" And she says, "No, but it's accurate." And it's
there's a deeper truth.
There's a deeper truth, right? And I think if you know that people are deliberately going to misunderstand you, I personally, as a science writer, as a science communicator, I would err on the side of just saying no. And if someone asked further, I would say, if you want a more complete answer, you can go here. I think some journalists caught on to that. The local Fox guy, Hal Eisner, was very careful to say, physicists never say never. They just don't. But in fact, it's not. It's not going to happen. No. Just because they're hedging and saying, well, there's a tiny, tiny chance. What they mean is no. So you can actually still say the physicist said this, but what they mean is no, because your job is the interpreter. And I think sometimes we forget that. That science communication in particular, you need a little bit of that translation going on, and that you are in fact a translator, and it's kind of your responsibility to make sure that things don't get misunderstood. A really good translator, a friend of mine translates books from English into Spanish, and it's a tough call sometimes because certain things don't translate well, in the same way that a mathematical concept does not translate well into a verbal concept. Something might not translate well from English into Spanish. So you've got to play around with it. You've got to tweak it. You've got to decide how to phrase things, where to depart from the original text. You've got to shape the narrative a little bit. And that is perfectly appropriate, in my opinion.
I think there's a challenge that journalists have, because there's this distinction between conveying understanding of something and conveying the impression that someone has understood something. And especially in very esoteric science things.
Right.
There's a whole bunch of explanation-sounding things that people would listen to and go, oh yes, I understood that. But the point is that the thing that they understood is not the truth.
Right.
and I got into this trouble talking about the Higgs boson with reporters before the LHC turns on. And there was this guy who said, this piece of popcorn I have in front of me, so what you're saying is, if it weren't for the Higgs boson, the particles in this piece of popcorn would not be able to stick together. And I said, no, actually I'm not saying that. I'm saying that without the Higgs boson, the particles in that piece of popcorn would all move at the speed of light, and they would zip off very quickly. And to me, I thought that was equally good or bad. But he didn't like that. He's like, can we just say stick together? Is that okay?
Right.
And I didn't. And I understand the temptation, but I'm not sure what good is ever done by making people think they understand something if they don't really understand anything more than they did before.
Well, I mean, it's very difficult, and I think it's an ongoing learning process. When I look at how I used to explain things 5 years ago and how I would explain the same concept now, I've learned through trial and error what works, what doesn't. Through constant repetition, I've come up with better explanations for things, and I think scientists do the same. The more that they interact with the media, the more they catch on and sort of get a sense for what works and what doesn't. We're getting better at it. But
and being a science reporter is also a specialized skill, and a lot of people who are talking about the LHC were not even really science reporters.
Right. And that's actually another big part of the problem, is that there's such a huge gap now between scientists and the general public, including very bright people who are reporting on the news. It's not something that really impacts their lives at all. They don't really stop to think about it. They're thinking about, gas prices and, the movie that's opening up next week. And
well, I'm thinking about the collapse of our global financial economy right now, but I don't understand it at all, and I really very much rely on people who are mediators between the two.
And there's some actually very, very good economics writers out there, but even so, we have to accept that there's only so much we're going to be able to understand. They're actually going to have to translate for us and put it into a lying to children kind of format for people who are not experts in economics to really understand. All I know is I'm drawing all our money out of the savings account and putting it under the mattress. Don't tell anyone.
But while you're doing that, I understand that you are taking on quite a task of your own in your continual drive to understand the minds of scientists better.
Yes, I am. And
what is that?
Yeah, again, really ham-fisted segue. Way to go. I mean,
you're not paying me enough to give me my good segues.
But I am just starting writing a new book. About a year and a half ago, on a whim, it was kind of one of those late-night infomercial kind of things where I happened to see an ad from the teaching company for a series of lectures on calculus made clear, and I had never really learned calculus. Former English major, became a science writer, and I've done pretty well. You know, I do actually, get a lot of basic physics concepts, although my education has been, as a self-taught person, you end up being very hit and miss. But calculus and math has always been something that I'm definitely one of those people who they see an equation and we just run screaming in the other direction. And
calculus might be the word that really is most evocative of people's fear of mathematics.
Yeah, I think so. I mean, there are other things as well, but calculus kind of sums it up. I mean, people just have horrible impressions of calculus. They usually had a terrible experience in high school, and we were all just so relieved to get out of that and never have to look at a mathematical equation again. But I decided to try and learn calculus, and the result is the book I'm working on now, which is tentatively called Dangerous Curves, How I Learned to Stop Worrying and Love the Calculus.
I like that title.
Yeah. And there is actually a connection to black holes. I mean...
but also, before you say that, let's get it out there that if Oprah Winfrey wants you on her show, you would say yes, right? Once you write the book.
I deign to be on Oprah's little show.
Let's get Oprah there, okay.
Yeah,
maybe even Ellen, or The View.
Or something like that. I actually might enjoy The View better. I really like The View. I think that they're a bunch of sharp cookies there.
They ask tough questions.
They do ask tough questions.
I don't think you want to go.
I like the challenge, and I also, I think that a lot of people like me, I think it's important that someone like me is writing this book. I read a lot of popular physics and popular math books, and they're always written by, the experts, which is good. I mean, don't get me wrong, we need
the
those.
Enthusiasts, yeah.
You need the enthusiasts, and definitely, you want these things to be accurate. But there's something that someone like me can bring to it, which is, I kind of know what it's like to be afraid of math, and I'm hitting, as I've been learning this, I've been hitting all the usual roadblocks that everyone always hits. Getting hung up on this notion of the limit, this idea that 0.9999 into infinity actually equals 1, which is ludicrous to those of us who never really went beyond, advanced algebra or trig. And we just don't get it. It just doesn't make sense, and it takes a long time to break through our resistance to that idea. And
well, it took Western civilization hundreds of years to work that idea, starting from Zeno and the Greeks and Pythagoras until Newton and Leibniz.
I actually felt a little better when I heard about that. I said, well, it's not just me.
No.
It actually took, humanity a long time to come up with this.
That's right.
But there's a lot of great stories involved, and when I really started looking at calculus and figuring out what it was, which is basically just a tool. I mean, it's just something that we use to solve problems. I mean, it's a little bit more than that, but for someone like me, I think it's more useful to think about it as a tool.
Yeah.
And then I thought, what would be more useful than trying to follow textbook problems and examples, which, even though they call them real-world examples, they're very idealized real-world examples, to try and create my own problems. For instance, you and I went to Vegas. And we
did go to Vegas.
I actually blogged about this because one of the things I wanted to...
You didn't link to your blog post.
Yeah, I will probably link to my blog post on this, but I wanted to talk about probabilities. And of course, a casino is a great place to talk about probabilities. Sean and I went and we took a craps lesson. New York Casino has every morning at 11 a.m. you can go and get an hour-long tutorial on how to play craps.
I like product placement. We should get some money from
I should.
New York, from MGM.
But I really liked that. And then right afterwards, they opened up a low-stakes table so that all of us neophytes could go and all learn to play our first game together and not be afraid of losing our shirts the first time out. Right. We did, in fact, collectively end up with $150 a head, I think.
We won, yeah. More than that, I think.
No, it was about $150, and then someone who shall remain nameless lost it on poker.
I won more than you did playing craps.
Yes, you did. Yes, you did.
But I like the fact that the people who were the instructors at the craps table were unambiguous about the fact that you will not win. There's no system. You cannot beat it. that in the long run, the house will always take its percentage. They were not trying to hide that.
No, and knowing perfectly well that people are still going to think that they're lying, that they can beat the house. I liked the guy, the second guy that was teaching us, because he was clearly, he was from Brooklyn or Jersey or one of those things, and he was like, "You think you're going to beat my table?" We got ATMs all over the casino for people who think like you.
And you got some good stories for the calculus book.
I got some great stories, including the where the term 86 came from. Essentially, if someone, back in the days when the mafia was running the casinos, if someone was a problem, he would tell his henchmen to say, "Take that guy 8 miles out of town and bury him 6 feet under." Hence the term 86.
I'm not sure if I completely believe it, but it is a good story.
It's an awesome story. Legend counts.
It should be true, whether or not it actually is.
In the same way that the LHC became the machine that could have destroyed the world, 86 will now forever in my mind be associated with Vegas casinos.
So who are we going to get to buy this book?
I don't know.
Not just because it's your book, but how do you get people who
are afraid of math?
Walk over to Borders or Barnes & Noble thinking, I will buy a math book now.
No one is. Now, the people that I want to reach are not the ones who are going to just wander over. In fact, you and I were in a Barnes & Noble just a few months ago in Santa Barbara, and you held up a math book, and you noticed my first reaction was, ew, math.
There's math in there.
There's math in there.
Yeah.
And I need to overcome that. It was a real wake-up call for me. This is going to be a hard sell.
That's right.
But I'm hoping the real-world examples will help. I mean, for instance, people who know anything about probabilities will immediately think, well, okay, the calculus of probability is very, very, the probabilities of craps is very interesting, but technically it's not really a calculus problem.
You could get by without calculus.
Right, you can get by without calculus. So how do we turn that into a calculus problem? Mm-hmm. And you and I could kind of batted some ideas around, but my favorite one was you basically figuring out how to turn it into an optimization problem. How do you get the most fun for your money? And
we're going to maximize our fun.
Maximize the fun, which of course means you've got to define all these things.
Yeah, you have to differentiate your fun and then set it equal to 0.
Right. And, essentially, to me, the most fun means that for a fixed amount of money, you play as long as you can. Because the fun comes and you get to roll the dice and cheer and this sort of thing, and you kind of want that to go on.
That's right. And then given those constraints, you can figure out... And I think that the nice thing about it is that forgetting about how to do a homework problem, if the book succeeds, it can help people understand sort of a mathematical way of thinking about the world.
That's ultimately what I'm going for. People keep saying, what, you're going to try and teach them calculus? And I would, no. I'm not trying to teach them calculus. I'm trying to teach them to think mathematically, to think in a different way, to basically see that this is not something abstract and removed from our daily existence. It is intrinsically bound up in it. And for me, the big telling point came when I was writing the first book, Black Bodies and Quantum Cats. I used to go into my editor at the American Physical Society, and I would have questions. And we would have our little 10 to 15-minute tutorial session where I would say, well,
he was a physicist.
Yeah, he was a physicist. His name's Alan Chodos. He was at Yale for a very long time. And now he's with the American Physical Society. And say, for example, I would say, well, I'm reading this physical concept. I know because I've been told that, objects, fall at the same rate, regardless of weight, regardless of mass. And I says, well, how did they know that? You can't really do the experiment in the vacuum, blah, 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 blah. And he showed me the equations. And initially I was kind of, ew, math. But when he walked me through them very carefully, and it's not tough, it's just basic algebra, and he showed me how the M cancels out. Mm-hmm. And the fact that this abstract thing, and you can actually work this problem and then have it reflected in the real world, it's like a light bulb went off in my head.
Yeah.
And I want to do that for other people, and also we've got to get over our knee-jerk antipathy towards physics and math, because I don't think we can afford to be afraid of it any longer. I mean, it's pretty much in everything now. Our entire 21st century culture is tied up in math and science, and we cannot afford to let people continue to be afraid.
Well, that would be nice, but I don't think that's going to be an effective PR strategy.
You're trying to plan my PR strategy?
Yes, of course. But I think the question of PR strategy is an important one for all of not even just all of science, but all of intellectual life.
Maybe I could say that calculus can destroy the world.
If you don't learn calculus, it could destroy the world.
Yes.
But I think we have to use more carrots than sticks, in other words.
Mm-hmm.
Instead of saying, you need this to understand the world around you, I think we have to be about why this is fun. It's cool to understand these
which
things.
is why we went to Vegas.
That's right. We did not suffer for our art very much.
And I believe in it. I'm taking you to Disneyland next.
I'm scheduled to give a talk to the theory group here at Caltech on the theory of poker.
Really?
At some point. So maybe that'll be a book.
And what is your theory of poker? I mean, this I think we've got about 10 more minutes here. I think we should talk about the theory of poker.
Well, I think, poker, of course, is a game with probabilities and so forth. And it's a game that is subject to the rules of game theory, but it's not solved. We don't know. So the rules of game theory tell you that there will be such a thing called a dominant strategy. A strategy which, if you played it perfectly every time, then nobody could ever beat you in the long run. You could tie in the long run, or you could win, but you could never lose, as long as the rules are symmetric for everybody. But no one knows what the dominant strategy is, so that's not very, very helpful. You can only solve the problem in very, very simple circumstances. So it turns out that the way to play poker involves inventing a model of your opponent. You believe that in this circumstance your opponent will do a certain thing a certain percentage of the time, and a certain other thing another percentage of the time, etc. And different opponents have different models and so forth, and then you need to apply your mathematical knowledge to that model of the opponent, and that's how you win.
Okay.
It's a little bit vague.
That is a little vague.
You need some equations to really give it. When someone raises you, what is the correct response? If you know that this person is a maniac, and they raise all the time, no matter what they have, then you can either call or re-raise them with quite mediocre cards. If you know that they're a rock, and they never raise unless they have pocket aces and have a very good chance of winning, then you know to fold. And that simple concept, extended to a huge, bewildering variety of circumstances, is the right way to invent a theory of poker. But just like in physics, I am a theorist, not a experimentalist. So my theorizing about poker is a lot better than my actual practice.
Well, you're dealing with the human factor here, and humans are kind of innately unpredictable.
Well, in fact, it turns out that the math involved in poker can get quite elaborate. I mean, both if you're trying to prove theorems about things, then high-powered math is involved, the geometry and topology and so forth. But if you're playing poker, if you're sitting there, you don't care about theorems, you just want to know, should I fold or not, then there's no high-powered math in terms of calculus and so forth, but there is high-powered arithmetic. You really do need to sort of add up a lot of numbers and compare them to a lot of other numbers. So a real good poker player, when you see them on TV, sitting thinking about what they should do, they're not thinking, I wonder if he's bluffing. He was scratching his nose, then I think therefore he's bluffing. They're thinking, if they have two hearts in their pocket cards, then there's a 16% chance that they're going to hit the flush on the river. My expected winnings if I call this bet, or blah, blah, blah. And they're doing math in their head.
Are they really?
They are absolutely doing math in their head, yes. Pot odds calculations and implied odds calculations and so forth. And that's why it takes them a long time sometimes. And the big flaw in my own poker playing is that I'm too impatient to do the math, and I sort of make a guess at it and later go, ooh, no, that was probably not right.
See, and most people would be surprised by that. They would think that, with a strong mathematical background, because, there are a lot of poker-playing physicists. Michael Binger came in third a couple years ago.
Physics is a very natural fit to poker. The sort of thought processes are actually very similar. But there's different kind of physicists and there's different kinds of poker players. And I'm not an especially good patient calculator, so I think that my poker is going to remain recreational rather than remunerative.
Well, it's probably better than mine. I mean, I'm very predictable as a player. Essentially, I go into play poker, and I'm fine at first, and then everybody figures out that I'm one of those solid players, and I only raise when I've got something, and then I can never get anyone to go all in. So. And
this should not be revealed when you write your book, because then everyone will know. But poker will certainly be mentioned, I hope, and other things, other good examples that you're going to have in the book?
Well, I'm going to be talking, obviously we're doing the basic road trip to Vegas.
Gas mileage.
For gas mileage and this sort of thing. Definitely going to be doing something like that. Among other things, I was really intrigued by something you said recently about, upgrading your mileage from, say, a 20-mile-a-gallon car to a 40-mile-a-gallon car.
Mm-hmm.
Is great, but there's not as much difference if you get 30 miles a gallon and then go to 40.
Right.
So that might be, maybe look a little bit at one of those sorts of optimization problems and turn that into it. But you can also, the road trip, the long flat road, is kind of the standard textbook example for teaching the basics, the two basic concepts in calculus.
Mm-hmm. So you're accelerating, constant rate, blah, blah, blah.
Right. And then from there you can kind of get more complicated and develop. So I'm starting out very, very simply in the book, and then we're going to be doing some Newtonian mechanics, which is why I'm taking you to Disneyland. I'm going to be talking a little bit about epidemiology, economics, diet and exercise and body temperature and fevers, thermodynamics, essentially.
I think epidemiology and plagues and things like that and epidemics, it's a great example because that is the real world and people know that.
Exactly.
If you think about it as a math problem, it's a little bit different than if you think about it as scary headlines.
Right, and for me the fun part is coming up with my own little problems, because the act of creating your own textbook problem means that you kind of, in the same way that you understand crosswords better, once you create your own,
right.
You actually understand the equations better and how equations work once you go through the exercise of creating your own. And then you start to understand what they're getting at in the textbook problems a little bit faster, because I think that's where a lot of us get hung up. It just, there was a blog post recently where the guy was saying that he had a student who essentially asked, okay, well, you want me to solve this according to how you think of the real world or how I think of the real world, as it actually
how
exists?
A scientist thinks of it, yes, or how the real world really is.
We have to learn to think like physicists. We have to learn to think like scientists, and that's a little tricky.
Right.
So.
All right, well, that's a very good point on which to say you should get back to writing your book so we can make millions of dollars after you go on Oprah.
Yeah. So, I hope you're not relying on that, because
I'm totally relying on it. Are you kidding me?
This is math.
Looking forward
People
to it.
don't like math.
Not yet.
So hopefully they will, because I'm actually, I wouldn't say that initially I really enjoyed crunching the numbers or anything, but I'm actually really enjoying watching things come together in the concepts. And I'm particularly having fun finding out how to apply them.
Everyone knows that you only learn things by teaching them.
Exactly. So, it's kind of, kind of learning calculus inside out, but it actually has been working for me.
So what we really want is for all Americans to write their own calculus book.
But only after I write mine and everyone
After you
buys
write
it.
yours, start a trend.
Yeah.
All right, it sounds very good.
Anything else?
I don't think so. I think that between the LHC and calculus in Vegas, we covered all the big stories of the last week.
Right. Because there's nothing else going on.
Yeah. But we'll be back.
We will.
Talk about other things. All right, so goodbye to everyone out there in Blogging Heads land, and I will see you there.
Okay, bye-bye.
Bye-bye.